Anyway, we had this matrix, which represents the Fibonacci iteration, and we found eigenvectors of it and used them to form a change of basis matrix, raised it to the nth power in the diagonalized basis, and then came back. And that, remember, it had some square root 5s and stuff in it, and they showed up in our final answer.
So after you raise like the matrix to the nth power, how did you do that? Did the whole
you just
multiply it out?
You just multiply again.
Okay.
Right. This was equal to p, and then it was like phi 1 minus phi, something like that, p inverse. Where this p matrix, I don't remember what it is, but it's something. And the point is that you just multiply by p inverse to work out what this is. I mean, you just do the matrix product. It's just three matrices. You know, invert p, stick that over here, and then just multiply out the three matrices. If you had a particular vector and you were like following it around that diagram, you would first multiply by p inverse, then multiply by this, however many times you're supposed to, and then multiply by this, and that'd be your answer. Actually, maybe what we did was more like that. I think we did have a particular starting vector in mind. But anyway, the point of that picture is that it's supposed to simplify moving around the picture. If you want to, right, so the picture looks like this. This p inverse, that's p, that's d, and that's a. So a equals pdp inverse. The point is that if you want to move around this picture, the matrices are telling you exactly how to do it. Just multiply by the matrix that has that arrow labeled, and that moves you around the picture. And if you want to trace an arrow in reverse for some reason, you just multiply by the inverse. Yes?
Are we going to like explicitly be asked to produce like a chain of coordinates matrix?
Maybe. Just come up with the eigenvectors, put them in columns. That's it.
Not like for this kind of thing, but like for just any to like change of basis. Because like in the textbook and like in class for a little while, we had like the B to C like kind of notation, which.
No, I'm not going to do that.
Okay.
In principle, I could, but I won't.
I'm checking.
But the reason is that personally, I think it's easier to not mess up if you don't do that in a matrix way. Work directly from the fact that the coordinates of a vector with respect to a particular basis are the weights you need to represent that vector as a linear combination of that basis. That idea is the fundamental idea, and if you work based on that, then you won't make these like switched errors where you're like, oh, it was supposed to be rows and I made it columns, or it's the other way. But whatever. The point is, you can get confused between P and P inverse, or between rows and columns, or between all sorts of random stuff like that if you're trying to use a matrix. But if you just work directly from the definition, there's no chance to mess up in any of those particular ways. I mean, basically, we put things into matrices precisely because that makes...
Show the determinant A is equal to the product of the eigenvalues in two different ways.
Right. Yeah, people found this one tricky. So if A diagonalizes to a matrix, a diagonal matrix with lambda 1 up to lambda n down the diagonal, then the determinant of A is the product of the diagonal entries. And one really easy way to see that is just apply determinant to both sides here. Determinant A equals determinant P, determinant of that diagonal matrix, and the determinant of P inverse. And then determinant of P times determinant of P inverse is 1. And then the determinant of that diagonal thing is just lambda 1 times lambda n times all the stuff in between. That's the easy one. And solution 2, which is relevant on one of the practice test problems actually, is to write out determinant a minus lambda I, so the characteristic polynomial, so when you calculate the determinant of this matrix, you're going to get lambda. What's the biggest power of lambda you're going to get? Lambda to the n. What's going to be the coefficient of lambda to the n when we work all this out?
-1 to the end.
Yeah, that's right. It's going to be either plus or minus 1, depending on the parity of lambda. In other words, you get a minus lambda from every term on the diagonal. That's the only Rook arrangement that has n lambdas in it. So that's going to be the leading coefficient. And then everything else is going to be lower order. All right, and you're going to get some constant term at the end, which is the product of the diagonal entries. No, sorry, it's just going to be the determinant of A, actually. But anyway, it doesn't matter. This is what's important. But we also know that the determinant of A minus lambda I is the characteristic polynomial, which means that it factors as lambda minus the first root times lambda minus the second root times lambda minus the last root. Right? If the characteristic polynomial has lambda 1 up to lambda n as its n roots, then the polynomial has to equal this factorized version. Except we don't know what the constant is, so we have to put a c out front. And then, well, what does c have to be actually? So if I multiply out this stuff other than the c, I'm going to get lambda to the n plus some lower order terms. And that has to match. These polynomials are equal to each other. So this leading term has to equal this leading term, which means that c has to be what? Yeah, it's got to be negative 1 to the n. All right, and then once we know that c is negative 1 to the n, what can we do to find determinant of A based on this formula? What? The hard work is done. So we're looking at this formula, and we know c. C is not unknown anymore. And we want to find determinant of A. What can we do?
Set lambda to 0.
Just set lambda equal to 0. So we get C times 0 minus lambda 1, which is minus lambda 1, dot, 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 minus lambda n. So that's another n factors of minus 1. Altogether, we have 2 n factors of minus 1. That's an even number of minus 1s, which is the same as no minus 1s. And then we have the product of all the eigenvalues. So the determinant is the product of eigenvalues. And geometrically, that makes sense because geometrically what the transformation is doing is scaling space by each factor, lambda 1, lambda 2, and so on up to lambda n, by the given eigenvalue along each factor. So as it scales by lambda 1 along the first axis, it's multiplying volumes by lambda 1. And then when you scale by lambda 2 along the second axis, it's multiplying volumes by lambda 2, and so on. Once you get done doing all those scalings, then you're multiplying volumes by the product of all those lambdas. So that's, I guess you could say that's a geometric proof as well. Yes?
How'd you get the plus something to the lambda n minus 1 all the way down? Where'd that come from?
The point is that there are no other lambda to the n's. That's all it's saying. I mean, maybe the something is 0 and that term isn't there. That's fine. But the point is that this is a polynomial in lambda. It's degree n, and the leading term is going to just come from those diagonal, multiplying those minus lambdas on the diagonal together. There are lots of opportunities for lambda to the n minus 1 to show up, but we don't really care what that is. We're just going to say there are some other terms, but we never ended up using them. Yes? This is the fundamental theorem of algebra. It says that if you have a polynomial and you know what its roots are, the polynomial is equal to some constant times the product of x minus root 1, x minus root 2, dot, 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 x minus root n. I mean, actually, the fundamental theorem of algebra says that every degree n polynomial has at least one complex root. But then you can expand it a bit and make it a meta theorem that tells you there is at least one complex root. You can factor it out, and then you can keep going, factoring out complex roots until you get down to a constant polynomial. And then your original polynomial is going to be equal to this factored form, which is some constant that you don't know, times variable minus first root, variable minus second root, and so on. That's the sound that means it's time to go.